Hello, my name is Jeffrey Altman. I am here today with David Howells. We're going to give you a presentation on AuriStor's next generation AFS and the Linux Kernel AFS implementation. This talk is a follow-up to my 2010 SDC talk on OpenAFS and the reasons why OpenAFS was still around more than 20 years after IBM released the product, their commercial product, as open source. This talk, now 10 years later, describes the future of AFS as it has developed as implemented both in the Linux kernel and by AuriStor in its vision and commercial product, AuriStor file system. You can take a look at the slide deck from my 2010 talk using the URL at the bottom of this slide. As just a review, AFS, when it was created back in the mid-'80s, had a number of operational goals that are critical to the reasons why AFS is still important in today's ecosystem. It was designed for location independence, by which was meant that clients could access their data from anywhere at the time on campus, regardless of what building they were in, the students, faculty, or staff were in. And it didn't matter what architecture the clients or the servers were, that the data could be stored and accessed from anywhere. There needed to be sufficient authentication and integrity protection and privacy to permit or prevent students and curious staff and faculty members from being able to break and do bad things with the file system, tamper with their with homeworks, assignments, or research projects. There needed to be geographic replication of critical data to allow to ensure that data was accessible with good performance from different places on campus. Now, this, of course, we now talk about accessing data from not just different buildings in a corporate infrastructure, but perhaps different geographic regions distributed all around the world. And we talk about the distinguishing factors between internal deployments, DMZ, and cloud infrastructures, all of which have their own properties. AFS had an atomic publishing model by which it was capable of allowing users to build up multi-file directory tree hierarchies of information, and then make all of the changes of a particular data set available at one time to the consuming public, which is very popular for software distribution of configuration files, information, publishing of websites, and so on. It was the notion that there should be one file system for everyone, that you shouldn't need to have isolated islands of data in various places. Your data shouldn't be trapped on a single disk or a single machine. It should be accessible from anywhere. Fine-grained access control to allow different rights and permissions to be granted to different classes of users, not only based upon the role that the user played, but also based upon the data itself, which volume the data was stored in, which directory, and we've extended that in AuriStor to per object control. One of the things that developed out of AFS in the later years, in the later 80s, was federated authentication, the ability for different institutions, such as academic institutions, to use their own local authentication infrastructure to authenticate users to storage systems hosted by other parties. AFS also had a rather unique AFS macro that could be embedded into path components or into symlink components that will allow for platform-specific path resolution. One of the examples that I love to use is the timesheet program from one of my early employers. Being able to have a timesheet program that ran on Windows or Solaris, on Spark or Intel, all at the same path from the perspective of the end user, but different paths from the perspective of what actually got executed and evaluated. A platform architecture independence for the back end so that your data can move from one architecture to another. You could have servers, a mix of servers, some of them being Spark, some MIPS, some PowerPC with big endian, some with little endian, and your data can move and flow from one to the other without any application noticing or being aware of the differences. And finally, distributed administration, that all administration should be done over the network and should be able to be done in a platform independent fashion so that administrators could control and manage the data and troubleshoot, grant access, allocate new volumes, do everything that was needed to be done without having to sit in front of any particular console. It's still here, even 10 years further on. Institutions that grew to depend upon AFS find themselves for legacy deployments locked in. It's for the things that AFS excels at, there are no clear alternatives. The transition costs are quite large, and but from the perspective of the future of AFS, legacy deployments themselves are not a reason to keep it going. And so from the developers of a file system, we have to keep pushing the limits and coming up with new reasons why things for people to use to leverage it and deploy it. Some of the most recent deployments in the last 4 or 5 years are larger than all the deployments combined from the 30 years before that, both in terms of number of systems involved and the number and the quantity of data. AuriStor has focused on a number of areas of extending the AFS model. We've focused on zero configuration for clients to make things really easy for end users to deploy, an improved security model, protecting client caches from cache poisoning attacks, improved performance on the network and on the back end, scaling of the namespaces to allow for much larger data sets and to address things such as time limitations, enhance file system functionality to improve the ability of specific operating systems to have a behavior, a personality that is that of the local file system instead of the lowest common denominator of the network file system. And finally, we've worked with David to provide an out-of-the-box experience on Linux for accessing the AFS namespace. From the zero configuration perspective, the most important part is how do you find data? Well, organizations that deploy AFS cells can put their information into DNS via SRV records. And those SRV records, as demonstrated here, allow for a client to discover dynamically the location of the location services location on the network, and thereby gain access to the set of volumes and from them the set of file servers that host the objects stored in those volumes. But in modern clients, there's no need anymore for deploying a hard-coded file of location information for each of the cells. AuriStor and Linux now distribute this cell service information, but we do so as a fallback in case of DNS outages. It is not the primary source of data. Federated authentication is also automatically discoverable, where what particular Kerberos realm, for example, is the authoritative for a particular cell, can be derived entirely from the service principals for that cell, based upon the two-part service host principal structure that is used by GSS API. And so even without deploying any Kerberos 5 specific configuration, a client is able to resolve which Kerberos realm is needed to be contacted. And if the client's realm is capable of contacting that realm, that client's principal will be able to obtain service tickets and then tokens for authenticating to that remote cell. AuriStor has put a lot of effort into improving the security of AFS. One of the biggest investments is in the developing and leveraging the GSS, what we call the RXGK security class, which provides for a wide selection of authentication mechanisms that can be used. And the most prominent in use today are Kerberos 5, as implemented in MIT, Kerberos, and Heimdall and Active Directory, as well as the newly developed and GSS Secure Anonymous class, which allows for negotiation of shared secrets between anonymous parties to allow for secure private communication when mutual identity authentication is not possible. The ARCGK security class also provides for the use of modern crypto with AES 256, basically the whole suite of Kerberos 5 based encryption algorithms. It allows for the use of larger key sizes, and we reduce the key exposure by deriving from a base key multiple keys for each particular purpose, and then rekeying those keys as needed based upon length of time expired, the quantity of data that's been encrypted with that key, and as when a combination of secure anonymous authentication for cache managers or for users is in use combined with Kerberos authentication, we can do token combination, which in turn further derives tokens about private keys for specific uses. One of the things that we strive for is to ensure that a unique key is used for every new connection between peers. ARCGK also provides for authentication of more than one identity. In AuriStor's implementation, we have implemented this as a ordered identity list. The most common form of combined identity authentication is the authentication of the user entity with the authentication of the system entity. So for example, these two are coming from a Windows domain joined machine. The user that's logged in at the desktop ends up with a Kerberos principal for user at that domain, and the machine itself, which in this case has a name of desktop, gets its own Kerberos principal and authentication. Those two tokens are then combined, and key combination is used to derive a unique new key. And we can leverage this not only for authenticated users, but we can also leverage this for anonymous users as well, and thereby ensure that all communication from a client machine to and from a server is encrypted, whether or not the user has authenticated themselves. We've also extended the access control mechanism to support what we refer to as a user-centric constrained elevation model. In this model, we can grant a user more rights via positive ACLs through the combined identity match. So in the prior example, taking the user and the desktop, we have in this case any rights that would be granted to that particular user would continue to be granted regardless of what the identity of the server is. However, the identity of the server could augment the rights that are granted to the user. And we represent these extended multi-factor access control entries by referencing an unordered list of names on the left-hand side, which can be either the names of users or the names of individual entities or the names of groups of users or groups of machines. A particular entity is our access control entry is selected only if all of the names in the from the ordered list contribute and match at least each component of the access control entry. So in the example that's presented on this slide, the user would have to be a member of group of users, and the machine would have to be a member of group of machines in order for the list read and write capabilities of that last entry to apply to them. When compared to other security classes that have been used for AFS in the past, the ARCGK mechanism has these characteristics. From the most important from the perspective of things that have not yet been discussed is that max packets per call. Because of the ability to do rekeying, we are able to, with this security class, to support individual RPCs that have a much longer lifespan than that of the ARCGK authentic security class that has been used with AFS for the last 30 years. In particular, what this means is that volumes that have more than 5.6 terabytes worth of data can now be transferred in a single call using ARCGK when they couldn't be transferred using ARCGK. We leverage the capabilities of ARCGK to improve security, but we also have developed a set of security policies, excuse me, and maximum ACLs that we can apply to AFS volumes. What many people don't realize when they think about AFS, they hear of AFS and it has the word file system in the name. And so the assumption is, well, it's just a bunch of directory trees that have a list of, each directory has subdirectories and stores files and symlinks and other subdirectories. But AFS really is unlike many other file systems or network file systems, is actually an object store. The protocols that the clients use to talk to the servers do not convey file paths. They only convey file IDs, which are really an object ID, a combination of a volume ID, a vnode ID, and a unifier numeric value. And these object IDs, or these volumes that store groups of objects, each of them should be thought of as an object store. And so what we do is we treat these as containers on which to associate security policies and maximum ACLs. The security policy constrains the set of RX security classes and data protection levels that can be used to access the contents of the objects in that volume. They also, though, provide a set of restrictions on which servers a particular volume is allowed to be migrated to or replicated to. And this can be used as a means of ensuring that certain volumes stay in classes of servers that are guaranteed to enforce the required security policy for that class of data. The maximum ACLs that apply on the volume act as a restraint on the set of rights that can be granted by an ACL on either a directory or some other per object, or other object stored in the volume. So if you take a volume and your intention is to purpose this volume for human resources, and it's going to be storing personal information about employees, contact information, salary, maybe health information, you want to lock that down to a particular set of users, group of users that are permitted to have access to it. But you would still like to be able to grant those users the ability to implement finer-grained rights and distributions of those rights among themselves without requiring that the help desk get involved. And so by leveraging these volume maximum ACLs, we're able to provide the organizational guarantees while allowing users to still have administrative rights for setting and managing ACLs on individual volumes. AuriStor has also put a lot of effort into growing the namespaces, so the object ID spaces. 32 bits just aren't enough these days. We need larger files. We need to be able to manage time beyond 2038, or if we're leveraging unsigned 32-bit time, 2106. And we'd like to be able to address finer grain granularity. And so we have done that with our time infrastructure, leveraging 100 nanosecond granularity, which matches NTFS, although we use the Unix epoch as opposed to the Windows epoch. Other areas where we've grown the space is in the maximum number of objects in a volume, the maximum number of volumes within a cell. The input, so for example, we are capable of storing 2 to 95 numbers of directories and 2 to 95 numbers of files in any particular volume object store. And we can have up to 2 to the 64 volumes, which is within a particular cell. The sizes of these spaces were determined based upon what would be necessary for a particular online sales marketing company or online retailer to be able to store information for every single product that they might ever sell. That was at least the intent. In order to improve performance, the vast majority of the effort, in addition to doing things on the back end, has been to improve our network stack. We are a network file system. In order to get higher throughput from clients to servers and to allow the servers to scale to vastly larger numbers of clients, we've implemented a variety of things. First, we've adopted IPv6 wholeheartedly. We are a UDP-based transport. IPv6, with its implementation for ICMP6, does allow us to perform path MTU discovery, which we are unable to do with IPv4, which is beneficial. We've implemented, we've studied and reviewed the last 20 years worth of TCP research and have applied many of the techniques and findings to our RX implementation. And this work has allowed us to increase the window size for a particular call from 32 packets now to a maximum of 65,535. From a file system operation perspective, clients issue RPCs to file servers. We have added, in addition to extending all of our RPCs to support our new larger object sizes, object ID sizes, offsets, lengths, etc., we've implemented new RPCs for new functionality. We now support, in addition to the advisory locks that have been supported for 30 years, mandatory locking. We allow for atomic file creation and locking. We've added a variety of rename variants, in addition to the AFS traditional standard of replace the existing target if it exists without question. There is now a no replace option that will fail the request if there is a target that exists, as well as an exchange option that will atomically swap to directory entries and objects. For data management, we've added an append data operation, which allows for data to be stored without knowledge of where that data is going to end up in the file, and instead to let the file server append that information to the end of the object stream and then return back the offset at which the data was located. We have, in addition to the traditional data store operations, where you specify a particular amount of space that is going to be written to, and then fill it. We also support now the ability to reserve a requested amount of space and then write as much as you can. And if you don't fill up the space, it will be truncated to the amount you wrote, as well as a reserve and zero fill option that will allocate a block of space and then take the amount of data that has been received, write that to disk, and then zero fill the rest. Finally, we've added some new server-side operations, probably the most important of which is silly rename. Is the ability, instead of having clients allocating when the last link to a file on the server goes away, directory entry goes away. A client needs to make sure that if it was stored locally, that file would not, that I know would not be destroyed right away until the last file handle or file descriptor was closed. In a network file system, well, in AFS, where we're dealing with an object store, there is no file handle that the file server is aware of. It doesn't know how many opens there are. And so the file server only has the ability to delete the object when the last link goes away. And so we use a silly rename technique to rename the file to a silly file name, one that is unlikely to be used by applications. And then it's the responsibility of the client to delete that file when the last local reference goes away. But this is problematic for a number of reasons. The client might disappear. It might get knocked off the network. It might crash. It might lose its authentication tokens might expire. All of which can leave behind these silly renamed files that the file server has, or object server has, no concept of when those objects can be destroyed. So in the new model, silly renames are allocated by the server, and the clients obtain a lease to them. And as long as the clients continue to renew the lease, the object will not be destroyed. But once the lease expires, automatic garbage collection can take place. We've also added some other server-side operations to allow for server-side copies, both of full objects and of ranges, as well as moving of objects from one place to another. At the moment, these are local to a particular server, but we hope to extend these in the future to allow for server-to-server operations. AFS has long had a history of being very successful at caching data for the long term. One of the reasons why AFS is leveraged heavily for software distribution or configuration management or even for distribution of content is because it allows for effectively hot caches to be constructed of ranges of objects that are frequently used by that particular client system. And as long as the data doesn't change on the server, the data version being incremented, then that data could be reused out of the local cache without requiring a refetch from the server. All that's required is that the client register a callback request, which provides the client the current data version number and a promise that until the callback expiration, the file server will notify it if the data is changed in any way. AFS has never had a security model protecting these callback mechanisms. That's one of the things that has been added in the AuriStor model, leveraging ARCGK as the security class for providing that protection. And we've also been working very hard to provide improved client experiences and user experiences. But one of the big challenges that AFS has always had is the lack of support in operating systems as shipped by vendors. And so David has been working for now almost 18 years.
Something like that.
Adding AFS support to the Linux kernel. And so, David, please tell everybody what you've done.
Next slide, please. So I've been working on a native Linux AFS file system driver with the idea that you can take a Linux box with a standard distribution kernel, and there's an AFS client right there. So there are several parts to this. One part is the driver in the kernel. There is a module that goes in user space that is, sorry, not a module, a package in user space that loads the module, starts it up, mounts the root of the AFS namespace and /AFS. It's all done under systemd, and then it's there every time you boot. Because it's a native client, it can be built by the distributions such as Fedora and Debian with all their other modules like ext4, XFS, and NFS, whatever, and then it's signed by their build processors, which means you don't get an annoying warning telling you that you've loaded an unauthorized module and that various kernel things like lockdep have been turned off. The driver supports most AFS features, and I've been working on adding support for AuriStor features. So it does IPv6, it does 64-bit file sizes, it does the 64-bit dates that the date and time stamps that AuriStor uses. So it's year 2038 safe if you're using with AuriStor. If you're using with AFS, you still have that problem to come. To set up AFS on, say, Fedora 32, you install the Kerberos 5 workstation package, so you can use Knit to gain Kerberos tokens, and you install the KFS client package. You can then set your the name of your local cell in a configuration file, and if you want to change the system name, you can do that too. But there are defaults to the system name. If you don't set a cell, it just won't have a home cell. Then you start. You tell systemd to start it, and that's one-off start. If you tell it to enable it as well, it'll then be around every time you boot. After you've done that, to do authenticated access, you do knit, and then you call the klogcafs program to get you a ticket. And then once you've done that, all your AFS accesses to the cell you've authenticated with are completely authenticated or are encrypted, authenticated. Next slide, please. So, you want to do this, Jeff?
Sure. Well, the AuriStor client and the OpenAFS client and the IBM client before that are all a monolithic cross-platform implementation. The same code base is used for Linux as for Solaris, for AIX, for macOS, various BSDs, the userland implementation that combine, of course, with platform-specific code, but it combines the file system, the network stack, and the data and metadata cache management all in one monolithic block. It also exposes AFS as a single disk or volume to the local operating system, which has proven to be problematic in various ways over the years.
So I've obviously taken a slightly different approach with the KFS module. Obviously, it's single platform. It only works on Linux, but it will work with any Linux architecture, even the no-MMU architectures. The design is modular. There is a separate module that is used by CAFs, which provides an RPC network protocol driver. You can, from user space, you can just open a socket of type RPC, and in using send message and receive message, you can create calls, send calls, and get replies back. I have some tools in progress that make use of this to provide the standard AFS toolset. There are other pieces that I've written. So there's local caching, which is shared with other network file systems, NFS, CIFS, AuriStor, and Plan 9. And it also uses the native Linux AFS locking model, because that's the only one you need to worry about. You just use it directly rather than being heavily Macerized. When it comes to dealing with what you actually mount, every volume appears as its own superblock. So this means that when you look in list the files in a under the superblock, you see the vnode IDs as inode numbers. DF, if you do DF on one of these superblocks, you get the correct values retrieved from the server. So if you've got a whole bunch of volumes mounted and you do DF, you see every volume with the available blocks and used blocks correct. I added auto-mount facilities to Linux VFS for AFS, but this is also used by NFS and CIFS and various other things. So what it does, if it sees an AFS mount point, it turns it into a directory with an auto-mount. When you step on it, it causes the superblock for the volume it points at to be mounted there. And this works cross-cell or within a cell. And you can manually mount any volume you like, anywhere you like, on any directory you like, provided you have appropriate authentication. And the way the authentication works is, once you've done your kinit and AKlog, it sticks a key onto one of your keyrings. And when you do a VFS operation or an ARCGK operation, it requests that key and then uses it for the cell specified. And next slide, please. So there's some advantages to being an external project like OpenAFS or AuriStor. Your code can be kernel independent, and in the case of OpenAFS or anything derived from it, it's already been ported to many different systems. And so if you want to add new features, you've already got the infrastructure to make these available to all those systems. And that means features or new AFS features can be developed there more easily, and then they can be rolled out faster because they're done within the project. And so everywhere the project can be compiled, the features can be pushed out. And an external project is a point of focus that someone who's interested in dealing with AFS can look at. The kernel, the Linux kernel, isn't a point of focus for people interested in AFS. It's a point of focus for people interested in hardware drivers mainly, and the kernel itself. However, being out of tree has a few disadvantages. The kernel internal interfaces change often. Perhaps I should say very often. And this is a problem because the changes are often incompatible, which means you need to add more and more glue layers, and configure needs to say, is it this particular minor version of that one? If so, this interface has changed like that, or that interface has changed like that. Also, parts of the kernel API, internal API, aren't accessible to external drivers that aren't licensed GPL. The internal CAS, being part of the kernel, can use all of these because it's the same license as the rest of the kernel. And another problem with being out of tree is every time the kernel advances a step, you have to rebuild all the modules for the different versions you want to support, times all the distributions you want to support, times all the kernels those distributions are currently supporting, which is a lot. And then the user needs to be able to find the packages wherever they are and install them for themselves. However, one advantage for CAS being in the kernel is there are lots of nice interfaces inside the kernel that are reserved, such as being able to use RCU, certain container features like network namespaces. So CAS can be network namespaced. So if you've got a volume in this network namespace pointing at server 1, 2, 3, 4, and another one in another namespace pointing at server 1, 2, 3, 4, these may go out, for instance, may go out different hardware network ports to actual different servers that happen to have the same IP addresses. There are also some shared components, so local caching and keyrings, which are used by other things within the kernel. There's a lot of available crypto in the kernel. Pretty much everything needs to do GSS API. So AES is there, Camellia is there, SHA-1, SHA-2564, SHA-512, and a lot of these have been audited by government services. Another thing the CAFs can use is the kernel's trace points facility. So CAFs has a lot of trace points for debugging. So you can turn them on and watch, for instance, packets going from particular calls going through the kernel. And then the kernel has a lot of debugging facilities like the LockDep and Kasan, which you can't use with out-of-tree kernels, at least. So with out-of-tree modules, not publicly. Next slide, please. There are other advantages to being in the kernel, just apart from just interfaces that are available. If a developer is going through making some big changes that touch all the file systems, they have to fix CAFs too. They have to fix NFS, they have to fix ext4, but for out-of-tree modules, they don't care, they don't touch them. There are lots of automated testing facilities. So if I have a branch on, say, a Git branch on kernel.org, I can push my changes to that, and various automated testing facilities will go and pull that branch and run tests on it. And then another advantage of being in the kernel is that distributions, so Red Hat, Fedora, Debian, will build the CAS module and other file system modules with the distribution kernel. They'll sign them, package them in their RPMs, and this makes them much more widely available because you just install your kernel, the file system module is there. You can then install the CAS client package, which is also part of the distribution, and it's set up, ready to go. Now this is only the client, not the server, and it's not there in any of the enterprise distributions yet. So it's not in RHEL, for instance. So there are some future CAS developments that I'm working on. First one of which is completely overhauling the local caching to use direct I/O inside the kernel. Currently, it uses a kind of bounce buffer, which is tricky and doesn't always seem to work right. Using direct I/O is a lot simpler and a lot faster, uses a lot less memory. Another thing I'm working on adding is a per container keyring. What this allows you to do is, if you set up a container, you can give it, the container manager can give it a hidden keyring, and the container manager can put keys into the keyring. The processes inside the container can't see the keyring, can't see the keys in the keyring, but the kernel can. So if the container manager mounts an AFS volume, say, inside the container, sticks an authentication key in the per container keyring, processes inside the container, if they access files in that volume, they will use the keys from the per container keyring without knowing that they're even there. This makes it easier for containers to do authenticated network access, network file system access, without without the processes inside the container having to do any sort of maintenance on the key. The container manager can keep the key up to date, refresh it, whatever. The stuff inside the container can just use it without even knowing they're using it. And last thing is adding the advanced AuriStorFS features, which any advanced AuriStorFS features which come out. So Jeff listed quite a few in an earlier slide. Most of them I haven't got around to adding yet. Some of them I have, as I mentioned, 64-bit files, 64-bit timestamps, and IPv6. Working on supporting GSS API, but I haven't touched most of the rest of them yet. Okay.
No, thank you, David. I think we are kind of running out of time, or actually have probably gone over time at this point. There are references to some of the information that things we've discussed at these URLs. The talk will be available on the SNIA SDC website. If you want to reach out to either one of us, please do so with questions or feedback. And please do take a moment to rate the session. We will get anonymized summaries from the conference organizers. I and David will at some points throughout the conference be online in the Slack room. If you see us, please say hello and let us know what you thought as well. Thank you.
Thank you.